Thanks for joining us today and welcome to our Let's Clear the Air virtual panel discussion on indoor air quality and needlepoint bipolar ionization. The IAQ industry has gone through some radical transformation over the last year in terms of the way business owners and consumers think about the air that they breathe. Indoor air quality has gone from a high-end amenity to something that's on everyone's mind. Ionization used to be targeted towards new construction projects for energy efficiency and is now an important consideration in any building with regards to pathogen mitigation. GPS has assembled an advisory board of experts in fields like virology, toxicology, chemistry, and physics to help inform our understanding of the hard science that plays into improving indoor air. I'd like to take this opportunity to welcome our panel of experts, including Dr. Sorrell, Dr. Farahi, Dr. Curcio, Dr. Sobek, and of course, Charlie Waddell. Today we are going to talk about the pandemic, the science of ionization, its safety and effectiveness. It will not be our last conversation by any means. As well, we will have future sessions that delve into these issues and some training opportunities available for you that I'll talk about more later. So with that, let's jump right in. So welcome, Dr. Sorrell. Would you take a moment, please, and introduce yourself?
Thank you so much for having me. My name is Erin Sorrell. I am an assistant professor at Georgetown University in the Department of Microbiology and Immunology and a member of the Center for Global Health and Science and Security. I'm a virologist by training and now focus on emerging infectious diseases primarily in the field.
So what is the role of a virologist and what does it mean to be a public health expert today?
It's a great question. I think a virologist can be anyone with basic virology training that works in the laboratory on basic research, developing countermeasures, developing vaccines, identifying and characterizing different viruses, as well as those that work in more generic public health spaces, advising policy, advising programs on how best to prepare and respond to emerging threats, specifically on viruses, of course. In terms of a public health expert, sadly, I think it depends on how many people follow you on Twitter these days. But I think that in general, a public health expert is someone who has a basic scientific training and can translate the information that they have to public for consumption and for use and advocacy and education. And so I think that expertise is critical in terms of understanding how to really translate the data into a consumable form so that we can, as a community, respond better to public health threats.
Amen to the Twitter thing. So from your point of view, what is the most important thing for us to understand with regards to the SARS-CoV-2 virus and the disease COVID-19?
It's a tough question. I think there's a lot of aspects of this particular virus that we're still learning about. We've learned quite a bit in the last year. One of the things that keeps me up at night is the long-term health effects that this virus has put on a variety of those that have become infected, right? Some people have very long-term consequences from infection that we're just starting to learn about, gain information on, and I think that's going to impact public health moving forward. Another aspect that I always worry about is the role of asymptomatic transmission. So individuals who don't present ill, who are still shedding virus in large enough amounts to infect other people. And that's why I think particularly this virus has been so effective in its longevity as a pandemic, because we have so much undetected transmission going on, not just here in the States, but globally.
So has your understanding of COVID-19 transmission changed over the last year? And if so, how?
Yes, and thankfully. I think it's something that the community, both in terms of, I think the general community, the scientific community, isn't giving enough credit, is the amount of knowledge and data that we've gained on this particular virus, on transmission dynamics. Just in this last year alone, there's been a number of fantastic research initiatives to better understand this virus, the virus family, and aerosol transmission. I think that we are learning much more about how viruses survive in indoor environments, how they transmit. And for this particular virus, and I apologize for sounding like a broken record, but the role of asymptomatic carriers in transmission and the role of variants variant viruses as they mutate, their role in continuing for this virus to circulate across the globe.
So what is the latest scientific information that we have on how COVID-19 is transmitted in and through the air?
I think that we're learning a lot about how the virus is surviving in the air, how it travels, and how it is able to infect individuals through that aerosol transmission. Initially, we were very focused on close contact, or what we call large droplet transmission. And now we're seeing that the role for aerosol transmission is quite strong for this virus, as other respiratory viruses have had a role in aerosol transmission. We found, I think the latest data that's been validated is that SARS-CoV-2 can survive in the air in an indoor environment for up to 3 hours. And that is going to vary depending on temperature, humidity, and air circulation in those environments.
So there's much more to mitigating risks indoors than just maintaining a 6-foot social distancing.
100%, yes. I think 6 feet is a minimum requirement in thinking about how best to protect ourselves and each other from exposure and infection. The use of face masks is still quite critical, and having proper air circulation, air filtration is huge.
So a very concerning topic is variants with regards to SARS-CoV-2. Can you tell us how many there are?
I can tell you how many I know of. There may be more on the horizon. There have been 3 major variants that have been isolated across a range of geographical locations and very close together, which is concerning because it shows that the virus is actually evolving in real time in different locations in a very similar way. There's a variant that was isolated initially in the UK, one initially isolated in South Africa, and one in Brazil. Most recently, there have been 2 variants that have been found in California. So all 5 of these variants have mutations in the virus that allow for what looks to be improved transmission. So the virus is able to infect even better than what we would consider the original virus. All 5 have been found in the US. Across a number of states. So these variants are here in the States, they're circulating, and they're, depending on our ability to sequence and characterize these viruses, we're finding them in an increasing number of states.
So of these variants that have been identified, which are the most concerning?
I don't know that I would put my money on one versus the other. I think they're all concerning because they show an increase in transmissibility. And I think the most important thing is that if we're able to contain transmission through a good, what we would call infection prevention control, social distancing, compliance with vaccine campaigns, if we provide an environment in which a large percentage of the community is protected, either from previous exposure to infection or through vaccination, there's nowhere for this virus to go in a human host. And so we can effectively push these variants out if we start proactively, aggressively preventing transmission.
So what do we know about the longevity of SARS-CoV-2? Is it going to be like the flu that comes around every year and changes a little bit but never really goes away?
It may. 6 months ago, I would have said I thought that was less likely. I think as we see these variants pop up, it's an indication that we are not curbing transmission the way we had hoped we could as a global community. And so I think what's important is it is not a national response, it's a global response to containment. And so without proper infection prevention control and transmission control of these variants across the globe, there's always a risk of reemergence. There's always a risk of additional mutations because this virus is prone to do that. So if we provide an environment where we have susceptible hosts, we will continue to provide an environment for the virus to mutate and for variants to arise. Not all variants are going to be effective. Some are going to disappear over time and others could take hold. That's what we see with influenza every year is mutations that arise that take hold and then become that next seasonal strain. There is the possibility for SARS-CoV-2 to do the same. And I think right now is our chance to try to prevent that both at home and abroad.
Is there any reason to believe that the method of inactivation of these variants will be any different than that of the original SARS-CoV-2 viral strain?
No, I don't believe so. The virus is still the same virus. It's just mutations on the surface proteins that allow it to have an improved ability to replicate or to transmit. But in essence, it's the same virus, same family, same subtype. And so there's no concern about inactivation of what we would consider that original strain versus any of the variants being any different.
Great. So please tell us a little bit about enveloped versus non-enveloped viruses and exactly what that means.
So viruses can either be enveloped or non-enveloped, and really what it means is how is the outer layer of the virus look? And so if we have an enveloped virus, typically that means it has some type of phospholipid bilayer or some type of surface membrane that covers the virus, protects the genetic information, protects the internal kind of workings of the virus itself.
Is SARS-CoV-2 an enveloped or non-enveloped virus?
SARS-CoV-2 is an enveloped virus, as is all coronaviruses.
So why are enveloped viruses easier to inactivate?
Envelope viruses are easier to inactivate because their envelope itself is actually sensitive to disruptions by detergents and alcohol-based solutions. And so when you're able to break through or disrupt that membrane surface, you can, in effect, inactivate that virus particle.
So it's my understanding that fomites, which would be considered viral material on surfaces, is not necessarily the largest transmission mechanism that's been identified so far from the virus to human beings. Is that true?
I think that is a fair assumption to be made. I think early on in the pandemic, there was a lot of focus on how were people getting exposed. Our basic understanding of coronaviruses based on the SARS outbreak in 2003 and then the MERS outbreak, which that virus is still circulating, but initially was isolated in 2012 in the human population. Our understanding of the way that those two viruses transmitted were much more of a close contact exposure and on different surfaces for a certain period of time. And so initially there was a lot of work looking at how long SARS-CoV-2 virus survived on surfaces and whether that was a route of exposure. I think it's one of many, but I don't think it's the primary route where people are getting exposed and infected. Interesting.
So other than SARS-CoV-2, what are some examples of enveloped viruses?
I think my favorite is influenza, and I think one that everyone can relate to is most people have either been vaccinated or have caught the flu. So all seasonal flu viruses, all influenza A viruses are enveloped.
So are bacteria harder to deal with and inactivate or kill versus a virus, and if so, why?
I think it depends on the individual bacteria versus individual virus. In general, viruses, particularly those that are enveloped, can be quite easy to inactivate, again, with that detergent or alcohol-based solutions. A number of bacteria also can be quite sensitive to those types of treatments. Trying not to get too technical here, there are some bacteria that create toxins that are very challenging to inactivate. But in general, I would say viruses tend to be more challenging in a closed environment to respond to.
So I'm going to put you on the spot. How long are we going to be wearing masks?
I think the jury's still out on that one. I think that the importance of wearing a mask continues to be very high and critical as we look at being very close, I think, to the end of this. As we continue to roll out vaccines here in the States, and as each state continues to get more and more supplies, as we now have 3 different vaccines, all 3 very effective vaccines, preventing hospitalization, preventing death, that are able to be used now across a large percentage of the population, is huge and is going to help us in responding. But in the same time, we still have a number of people who are susceptible and who could get exposed if we aren't using our face masks or wearing them properly. So I think for now, it's safe to recommend and really require face masks, particularly in closed indoor environments, until we get what we would consider herd immunity from this virus.
So with regards to achieving herd immunity, what percentage of the global population would need to be vaccinated to achieve that, and do you think it's at all possible?
Simple answer is we don't know yet. I do think it's possible, but it's going to take some time. Herd immunity, our percentage of the population that we would need protected either from exposure and recovery to infection or through vaccination, is contingent on the transmission rate of the virus. And so CDC and WHO are right now investigating the number that they feel would be the required percentage of the population that would need either type of coverage, ideally vaccination over recovery of infection, to have herd immunity. We as a nation are tides ahead of others in terms of being able to vaccinate our population and have that herd immunity in the US. But from a global perspective and global distribution and equitable allocation of vaccines, that is going to take quite a bit of time.
So what effect will the COVID-19 vaccine have on our concerns with indoor air quality? I've had both my shots and I'm still considerably nervous. Put my mind at ease, can you?
I'll try. Congratulations on having your vaccine. That's fantastic. I think that indoor air quality is critical regardless of this pandemic. There are so many respiratory pathogens that are circulating on a seasonal basis, on an annual basis in our indoor environments. Flu is a perfect example. We have seen a very low, if anything, almost negative flu season this year in the States. And a lot of that has to do with the fact that we are social distancing, we're wearing face masks, people are working remote when they can. Many schools are remote, and so we don't have that environment that helps support flu to circulate and to transmit. Again, there are a number of bacterial species and even environmental hazards in our air, as my colleagues I'm sure have addressed, that impact public health and respiratory health from an indoor air quality environment. So I would say beyond this pandemic, the importance of having clean air in our environment in order to work, to live, to learn is critical, and can help prevent further outbreaks of other respiratory pathogens.
So would it be fair to say that all of us attending this webcast today are in a business that will have longevity well into the future?
I think yes, I do.
Dr. Sorrell, can you put my mind at ease and tell me the viruses, the mutations you're aware of, the current shots that people are receiving will be effective against those? Because the news has been very dodgy of those questions.
Yes, it's challenging because out of the 3 vaccines that have had what we call emergency authorization use by the FDA, 2 of them were authorized before these variants really came to light. And before they were isolated in the States. So the clinical trials for Moderna and Pfizer did not include their effectiveness against those variants. J&J, because they were a little later, were able to actually test. And they had some discrepancies in terms of the full protection, depending on the variant. That being said, every single one of the vaccines that we have on the market right now that are available for public consumption, 100% protect against severe disease and 100% against death. And so these are really fantastic vaccines that have really high effective rates. They're learning more and more, doing trials on both Moderna and Pfizer's mRNA vaccines to see how well they respond to the different variants. I think the key is trying to get as many people protected as quickly as possible so those variants cannot continue to circulate and that additional variants would not be able to continue to circulate. The nice part is the platforms where the vaccines were developed, if need be, could be altered to be able to respond more effectively to these variants if they become the dominant strain in the future.
Dr. Sorrell, I have a question. So going back to new strain development, the segment of population of the children, that's basically they have. I mean, I know some of the companies right now, the vaccine companies are looking at running trials and that type of thing. When do you think we'll have mass vaccinations of our children in the United States and other places in the world?
It's a really great question, and I think it's very different, the U.S. versus, unfortunately, the U.S. versus other parts of the world, just because of equitable distribution of the vaccine and the ability to secure allocated resources and stockpiles. So we know that I think roughly 80% of the vaccines that have been distributed globally have only gone to a handful of states, or I should say countries, right? And so there are many countries that have yet to even put one needle in one arm, and that is concerning from a global perspective because these viruses don't pick and choose borders which they cross and don't cross, right? So that becomes quite challenging. In terms of adolescent coverage, and I believe both Pfizer and Moderna and J&J are approved for teenagers, and I think it ranges depending on the vaccine between 16 and 18 years of age. And there are trials going on right now for younger children, even as young as 6 months of age. And so those trials have just begun to look at safety and then efficacy. So I think that we'll get that data in the short term here, at least in the US, and then be able to commit to vaccines for that population. We're seeing great data come out from women who were able to get vaccinated pregnant, that at least, again, this is very, very early on, that babies born to vaccinated mothers do have what we consider IgG antibodies, so that memory antibody to be able to respond and fight off infection. Jury's out on how long that will last, but it's great to see that there's been that transmission, vertical transmission, mother to child. What concerns me is global distribution. I would note, though, that younger children, on average, tend to be less high risk of severe infection and death from this particular virus. While it is important to understand how best we can protect them, they are probably one of the lower risk groups for severe infection and death.
As well, a virus is a particle, so a technology that can be effective at reducing particle concentrations may also be effective at being able to remove the virus from the atmosphere and the air that we breathe. Would that be a safe assumption as well?
Yes, I believe so. And I think particularly if we're able to decrease concentration of particles, particularly in an internal environment, the chance then of getting exposed to those particles, if airflow is moving and people are moving, is less. So the chance of having actual exposure to a virus that is getting minimized through ionization is quite important.
It most certainly would be considered an additional methodology of social distancing, right?
I would say yes, yeah.
So let's shift gears just a little bit and talk about the science of ionization. Dr. Farahi, you are the physicist on our panel. Can you tell us a little bit about yourself, please?
Yes, thank you for inviting me to this panel. Yeah, I study physics and optics, and my PhD is in optics. And optics is a branch of electromagnetic field in which we study the interaction of electromagnetic fields with matters. Therefore, within the context of today's discussion, my expertise deals with how electromagnetic waves, in which in this case electric field, interacts with matters and then produces ions.
How does your skill set specifically relate to indoor air quality?
Yes, my expertise is in physics and in optics. In the context of today's discussion, we focus on ionization technology, and there is a need to understand what is an ion and how it is produced. Therefore, these are scientific-based questions. If you have a particle that has a net charge, we call it an ion. It can be an electron, it can be an atom, it can be a molecule. But in general, most particles have zero electric charge. But if for whatever reason we see there are needs to use, okay, let me correct myself. Therefore, for whatever reason, if we think ions are useful for some application, then we need to think about how to generate them. And that is the domain that my expertise can come into play.
At a fundamental level, what is ionization?
An ion, as I mentioned, is anything which has electric charge. An electron is an ion. That means if you have an ion detector, and then you have electron in the space, it looks at it and measures it as an ion. It can be an atom, which is ionized. That means it has a net electric charge. Or it can be a molecule. Therefore, ion is a very broad term. And then ionization is the process in which these charged particles or atoms or molecules are produced.
Do positive and negative ions just cancel each other out?
The answer is yes and no. If they come to vicinity of each other, if you have two particles, which one of them is positively charged and one of them is negatively charged, and if they come to vicinity of each other, then there is an attractive electrostatic force between them that brings them together, and these particles come together and they make a larger particle. In that case, if they have equal charges but in opposite signs, then they cancel out each other. In terms of electric charge, they cancel out each other, but they form a bigger particle. And this bigger particle, okay, are typically or not airborne, or if they are airborne, they can be captured by air filters. That is why ionization can make, air cleaning possible.
That makes perfect sense. Thank you. How does ionization improve indoor air quality?
By bringing these smaller particles together and form a larger particle. Therefore, from that perspective, it cleans the air. Also, it has other impacts on air. For example, it interact with pathogens and can, depends on the energy of these ions that we generate, it can completely destroy the pathogen. But at the same time, if these ions are very high energy, they can also create ozone in the environment. They can, activate some sort of unwanted, reactions with, VOCs. Therefore, we need to see that in what are our target applications, and then how do we want to really control these energies in order to make sure that we clean the air without, having unwanted consequences.
So, Dr. Farahi, what is agglomeration and how exactly does that work?
Assuming that, in the air you do have various particles which they do have positive and negative charges. As mentioned before, when they come to the vicinity of each other, the electrostatic attractive force between negative and positive charged particles become dominant and brings them together and form a much larger particle. And therefore, smaller airborne particles which are difficult to filter out, suddenly they form a much larger particles, and as a result, you can filter them out, or they can even drop and they will be no longer airborne. And that is the way, it impacts the, air quality.
So what actually takes place with regards to the interaction between these particles as they are agglomerated? And how are the particles actually charged and attracted together?
There are different ways to ionize air environment. One is through, for example, UV light. But within the context of today's discussion, we are talking about ionization technologies, which they use high electric field to ionize the air. And the way it works, this high electric field frees up electrons from the metal in which they apply this high voltage to. These free electrons are highly energized. They do have kinetic energy. Therefore, they become particles which are moving very fast in the environment around them. These particles collide with other particles or molecules in the air. And then since they do have a lot of energy, they can break down the other molecules, for example, and they form atoms and therefore ionize them. They can even attach to a molecule and ionize them. They can attach to a dust particle and ionize them. Therefore, there are multiple ways to this ionization to happen. Therefore, this is really the presence of high energy electrons in the air which make this possible. Okay. Now, if the energy of these electrons are too high, then we can create plasma. That means we can change these these molecules into atoms. And that is when most likely there are some unwanted reaction happens. For example, ozone will be generated, or we will have unwanted reaction with volatile or organic compounds. But if we control this energy to the right amount, we can avoid production of ozones or unwanted reactions, but having positive impact in the air quality.
Are all ions created equal? Are some stronger or more reactive than others?
Yes, they are different, and the reason they are different because they are produced through electrons with different energies. If very high energy electrons, as I mentioned, for example, collides with an oxygen molecule, it can change it to oxygen atoms, and therefore it creates plasma. As a result, this becomes highly reactive. But you can ionize oxygen molecule with lower energy electrons, which is very good for the environment without creating ozone. Therefore, there are differences, and all depends on the level of energy you give to these electrons.
Exactly what in the air is ionized? Which atoms and which molecules, and what are they broken down into? Are there byproducts that are formed in this process?
Air is made of some 80% nitrogen, close to 80% nitrogen, and just a little bit more than 20% oxygen. And of course, in our environment, we do have other components, but the composition of air is primarily oxygen and nitrogen. Therefore, when we say that ionize, what we mean is that ionizing nitrogen and oxygen. As I mentioned to you, we would like to ionize them in a way that they keep their molecular form rather than make them atoms, so that they become not chemically very active.
So tell us a little bit about the different types of ionization. We know there's what's called bipolar ionization, or BPI. We know there's needlepoint bipolar ionization, or NPBI. And then we know there are other technologies that do other things that may not be as, as applicable to the commercial market as some of the others I just mentioned. Can you delve into a little bit of depth and help us understand the differences between those technologies?
Yes, the BPI, as a very matter of principle, and needlepoint bipolar ionizations are the same. The physics of it is the same. However, the way it is implemented are different. As a result, the impact in the air quality is vastly different. In bipolar ionization, not the needlepoint bipolar ionization. The bipolar ionization uses typically a conducting tube and then apply very high voltage. Therefore, the production of ions are very localized. And since the effective surface area is small, they need to use much higher voltage than needle point bipolar ionization is needed to produce electrons. In the case of bipolar ionization using needle point, there are, these issues are resolved because the effective surface areas are very large. As a result, you don't need high voltage to produce as much electrons. And also, the production of ions are distributed in multiple points. Therefore, the ion density is not that high, although the total number of electrons is high, but the ion density is not high. Therefore, the chance of producing ozone is much lower than the typical bipolar ionization.
So in the context of air quality, what's important to know about each of those individual types?
From the user perspective, it is better, they are producing, unwanted reaction in the air, whether they are producing ozone or not, because if you can avoid these, then what you have optimized your system to have benefit for air quality without, these unwanted chemical reactions in there. Therefore, that is why it is important. The good thing about needle point bipolar ionization is that you do have a control on how much electron and how much energy you can give it to them. As a consequence, you can adapt it to the need of the indoor environment rather than, and this flexibility does not exist in typical bipolar ionization.
So tell us about corona discharge. Does needlepoint bipolar ionization produce corona discharge?
Corona discharge is really, but it mostly relates to the traditional bipolar ionization. As I mentioned, because it is really, the energy is focused in one small area, therefore the energy density becomes very high, and as a consequence, around the discharge point, you do have a lot of plasma. In the case of bipolar, since, in case of needle point bipolar ionization, since this production and this field is distributed, therefore the field density is not very high. As a result, you don't produce plasma the way corona discharge produces.
What's been your experience exploring needlepoint bipolar ionization technology, and how do your first impressions differ now that you understand the technology more in depth?
It really didn't take me long to appreciate the potential of this needlepoint bipolar ionization for many reasons that I mentioned to, there are scientific reasons that this technology works better, because simultaneously, by the very nature of it, it does not create very localized, strong electric field. It is distributed electric field, and because of the increased effective surface area, it can work at lower voltage and also has the potential to adapt.
So we'll shift gears just a little bit and we'll talk about, is ionization safe? Dr. Curcio, welcome to our panel discussion. Can you take a minute, please, and introduce yourself to our audience?
My name is Dr. Larry Curcio. I'm a practicing toxicologist consulting for Global Plasma Solutions. My background started in toxicology at the graduate school level in kidney disease. I subsequently went on to work in the pharmaceutical industry, other chemical industries, and have been consulting now for approximately 20 years. The toxicology practice really is involving the risk of humans to a variety of different products and components that we can discuss going forward.
So now we're going to tackle the subject that we all want to know about. Is ionization safe?
Ionization at particular levels is absolutely safe. Ionization occurs, as Dr. Farahi has mentioned, occurs in nature every day. It's really a fundamental principle of toxicology that the dose makes the poison. Anything at a high enough dose can be a poison to the human body. What we're trying to do is determine the safe level and the non-safe level.
So what does a toxicologist do, and how does that relate specifically to indoor air quality?
A toxicologist is going to be assessing the risk to human health with several different components. It can be chemical components, it can be biological components, it can be physical components. In the case of indoor air quality, you're dealing with physical components, particulate matter, dust, dirt in the air. Biologic components would be microbes and viruses that can also be present in the air. And chemical hazards could include chemical components like ozone in the air.
What are the toxicological challenges of cleaning the air, and what is it we need to consider when employing technologies to try to accomplish that?
The most fundamental technology involved and the science behind the toxicology with the technology is you're trying to remove unsafe components from the air, and this can be mold, bacteria, viruses, particulates, at the same time as not introducing new products.
So UL 2998 requires a manufacturer's product to emit no more than 5 parts per billion of ozone into the environment. How far below levels of occupational concern is that threshold that the product has to meet?
It's an infinitely small amount. You can get ozone concentrations as high as 1,000 parts per million in the normal air, depending on how it's being generated. So you're well below, you're about, I think, 50,000 times lower than when you produce less than 5 parts per billion ozone through the UL standard test.
So in indoor environments, particularly those perhaps healthcare where you have immunocompromised individuals or schools with susceptible children, that would be a very important consideration, I'm guessing.
It's an extremely important consideration, primarily because ozone as the chemical can produce a variety of respiratory problems, including coughing, gagging, difficult breathing, shortness of breath, etc. So you want to minimize those as much as possible.
What's the relationship between ozone indoors and aldehydes?
Aldehydes and other chemical compounds are secondary formation reactions from introducing ozone with another chemical commodity like an aldehyde. And ozone, you can create formaldehyde, which is a notably toxic material.
So for products that have been validated to that UL 2998 standard for zero ozone production, is this still a concern?
No, because you're essentially removing the ozone that you would need to produce various aldehyde formations like formaldehyde. If you don't have one of the starting materials, it's difficult to end up with a resultant problem chemical like a formaldehyde or an aldehyde in general. One of the fundamentals that you're trying to establish with indoor ROS levels are, do you have ozone present to start creating these reactive oxygen species? In the case of the GPS needlepoint bipolar ionization equipment, as documented by the Underwriter Lab 2998 studies, you do not produce ozone. Therefore, the chances of producing reactive oxygen species are negligibly low.
What are the health impacts of us as human beings and our exposure to air ions? Is there any difference between ions that are negatively charged and positively charged from a healthcare perspective?
In the case of positive versus negative air ions, there's no discernible difference as long as you keep the levels of either ion to a reasonable amount. You see ionization occurring naturally, beaches, waterfalls, where you can create several thousand ions per cubic centimeter of air. You want to make sure that the levels indoors are not going to be excessive.
So would it be fair to say that negative ions don't necessarily make you healthy, nor do positive ions necessarily make you less healthy?
There's a lot of publications trying to emphasize that point, and that point is really not technically correct. I can create just as much havoc with the human body by throwing a lot of negative ions at the person as well as doing a very high number of positive ions. You want to have a balance, and that's what's most important.
So what would be considered a safe level of ionization from a perspective of ion concentrations per cubic centimeter?
Okay, first of all, understand that there is no safe level mandated anywhere in the world, with the exception of one Russian study where they found that 50,000 ions was considered to be safe for various occupational spaces in Russia. The US FDA, the EPA have not established any kind of regulatory limit of safety. GPS had asked my company to go in and perform a risk assessment on ions to come up with just that question, just an answer to that question, a safe level. By going through the various literature sources, by going through strong studies where various individuals were subjected to ions at very, very, very high levels, we're talking about millions of ions in the breathing space, we came to a conclusion that 50,000 ions per cubic centimeter of air would be considered a safe level.
Does that mean that 51,000 might be harmful?
No. You have to understand that in many of these studies, volunteers were exposed to hundreds of thousands to millions of counts of ions in various trials. The difference between 50,000 and 51,000 is absolutely negligible.
So in this topic, we're going to talk about ionization's effectiveness, specifically with regards to certain pathogens. We are going to be talking to GPS microbiologist Ed Sobek, who I will introduce in just a minute. I do want to let you know as well that in this conversation, you may see some slides appear in front of you that will tee up the conversation just a little bit better. I wanted to make you aware of that. Dr. Sobek, welcome. Can you please introduce yourself to the audience?
Thank you, David. Yes. I am the Chief Science Officer for GPS. My background is in microbial contamination of the built environment. I have a PhD in microbiology. I've been working in this field for 25 years, and I've come out of the world of laboratory. So running a laboratory, developing a laboratory, really focused on the whole side of detection, almost at a forensic level for microbes, where I adopted early on in our detection technologies DNA forensics. So microbes have DNA, nucleic acids, RNA for viruses, bacteria and fungi have DNA. We're able to use that to identify species and quantify the numbers of each of those species. It's really important to be able to get down to those levels. And so from that standpoint, I really have a lot of experience dealing with these different types of microbial issues in all these different types of facilities: manufacturing, cosmetics, food, residential, commercial buildings. So from that standpoint, I am going to be bringing a lot of that into the whole aspect of, we have ionization with GPS, we have this technology, how does it get applied from the standpoint of dealing with microbes in these different types of facilities, and to be able to control and make our indoor air environment much better than it is currently.
Can you tell us a little bit about what steps we are taking forward with regards to various experiments and design?
So moving forward, we're going to be doing a lot of different experiments with a variety of pathogens, and they're going to include molds, bacteria, and virus. So some of the things that we're looking at currently is actually working with the SARS virus, where we commissioned a series of studies in a biosafety level 3 laboratory. And so what we're doing there is we have a whole chamber set up so we can mimic the real world situation versus just having something on a lab bench, up really close with an ionization system really near a petri dish. That's really good to start off with on a phase 1 study, but we're further on than that now, and we need to be looking at what's going on in the space because we're treating the space, so that's what we want to focus on. So we have a series of experiments running. We're looking at SARS-CoV-2 and looking at the efficacy of ionization against SARS-CoV-2.
So when testing SARS-CoV-2 or any viral issue of concern in a petri dish, is that a credible test subject or study? Is that a recognized way to be able to test the efficacy of a technology against a viral issue of concern?
Well, getting back to the petri dish, it's from that standpoint, it's a starting point. So any new technology you're working with, I have a long history of working in labs. I've worked in labs for a very long time and doing testing of a lot of different products. A client comes in, they want something tested. Well, you don't want to design this elaborate experiment that has all these controls and all these treatments that's going to, have a huge cost to it if you don't know if you have any efficacy at all. So first thing you want to do is find out if you have some efficacy. And that's where the petri dish test comes in. And it's perfectly valid for doing that. And, you do it with the first steps on anything that you want to see if it has microbial efficacy. There's nothing wrong with that, but that is the first step. And after that, then you want to obviously progress to those more advanced experiments that are not just artificial laboratory benchtop experiments, but encompass, the real situation that we live in. The air we're breathing, the spaces that we're working and going to school and those types of things in.
So are there important things to keep in mind when you're comparing aerosolized test results versus surface test results?
Sure, absolutely. And going back to what I said a little bit earlier, the focus on that surface, and as we discussed, you have on the surface it's 2-dimensional. In the air, you have a 3-dimensional access to a viral particle. On a surface, viral particles tend to be clumped. Obviously, they're in droplets. They're in locations, and they tend to be in high concentrations. Whereas in the air, after you sneeze or things get picked up in the dust, on fomites and things like that, the airborne, it's dispersed and it's diffused. So if I have a sneeze and I have SARS-CoV-2, it's going to diffuse out. And in this room where I am right now is, we're going to have the concentration gradient. It eventually comes to equilibrium. So from that standpoint, you have different aspects of surface control versus air control. And, one of the things you would expect is that with the high concentrations on surfaces, 2-dimensional access to it, it's going to be regardless of what you're dealing with, whatever type of technology, it's going to be more difficult to eliminate all those active viral particles on a surface versus in the air.
So what are some of the major factors in test design that will influence test outcome?
So when we're dealing with, treating the space side of it, we want to understand what's going on in the space. We need to design our experiments correctly so we replicate. You need to have the correct airflow. Ionization, it's really important to be able to have your correct volumes on your fans and your velocities. So you're having a good ion concentration in the room. Or in this case, if we're dealing with obviously BSL-3 chambers, large chambers that you can stand up and walk around in, it's replicates a living space. We want to make sure we have the correct system set up for airflow in those conditions so we can actually move the ions throughout the room and come to, so we have, averages that we can measure. So we're at a normal distribution for concentrations in those locations. So that's important with that. When you're dealing with surfaces, we talked about things to be dry or wet. How again, ion placement, ionization placement, where when we're treating a surface and we're looking at that surface activity, again, you want to have look at the ion densities. We want to have those what you would typically find in a room. So you want your concentrations. We look at concentrations in the range from 10,000 to 20,000. So we don't want to be hitting it with on a surface with 150,000 ions per cubic centimeter. We want to have it at 20 or 10,000 in those ranges that we work in for efficacy against microbes, so we can test what we would actually see in a building.
So what's important is to try to replicate real-world scenarios as closely as possible, specifically with regards to the ion densities provided to the space by the NPBI technology mounted in the system.
That's exactly, David. That's exactly what we want to do. We want to replicate that. And so, when we see efficacy occurring and we have control and inactivation of the viruses on that side, we feel really confident the technology is working, and that allows us to take that and talk to our clients, and they can feel confident about what we're doing. I mean, that's really important.
So the most recent GPS pathogen testing was done in a BSL-3 laboratory test environment. Can you tell us a little bit about the different testing levels in laboratories and what they mean?
Sure. So BSL-3, basically, from that standpoint, that we have the whole BSL level. Let's just start with that. You have 1, 2, 3, and 4. Those are the levels. Level 1 is very simplified. You can actually work with a variety of different microbes that are not pathogens. They're common in the environment. They don't hurt anybody. You can work with them on the benchtop. Most university microbiology labs are, BSL ones, and those types of classes that you have in those labs, you're dealing with BSL-1 organisms. But as you move up, basically that BSL level builds upon itself. So BSL-2, as you get higher tier, you have obviously all the regs that you have to deal with for BSL-1, and then all the new ones with BSL-2. And it keeps building itself all the way to BSL-4. But when you're in a BSL-2, you're dealing with different types of, these are BSL-2 level pathogens. So you have some different types of bacteria and molds and viruses that, don't cause terrible infections, but they will cause infections. Some of them are opportunistic pathogens, and you need to take precautions with those. You need to work with those in certain situations. You have a lot of containment hoods with laminar flow. You have a bunch of safety things in place, but when you want to work with things like SARS-CoV-2, which is a BSL-3 organism, you have to have a BSL-3 facility, and that is even more stringent. And so, again, it builds on 1 and 2, so you're adding more controls in where you have empty chambers where you have to walk into before you can go into the main chamber, and all these things are sealed off. You have precise methods of decontamination after you're done with your experiments. So you have ways you transport your test organisms. All these different things come into play, and it's really important because obviously these things can be highly infectious, and you don't want a release of anything, and obviously you don't want your employees in those laboratories to contract something from working on it.
So people are always asking for real-world testing on viruses like this. Is that something that can actually be done in effect?
Well, yes, and that's the thing. BSL-3 with SARS-CoV-2 is not limited by size. You can build the facilities, and within that facility, you build a room, and obviously that room is sealed and contained and has mechanisms to get into that room. And, obviously a special HVAC system to control that room, but you can build these large chambers inside those rooms where you can put chairs in, couches, or whatever you want to put in there. From that standpoint, we're using an 8x8x20 out in our BSL-3 facility that we contract with. So, it's a large area, large space. It has basically an HVAC set up to it with recirculation, air's coming in, but that's all contained. So it's as close as to the real world as you can get.
So Dr. Sobek, can you describe to us some of the most recent testing that we've done and the type of chamber that was used to do that testing?
Sure. The most recent work we've done has been with SARS-CoV-2 in a BSL-3 facility in a 20 by 8 by 8 foot chamber. So this is, a large area that we can put tables in there, chairs, those types of things. We have basically its own HVAC system hooked up and contained to it. So that's running and circulating. And we've done, in that chamber, we've done both surface and air testing.
Can you describe the results that we've seen?
Yes, results are very encouraging. We're working at two different ion densities. And these are approximated, but we're at 10,000 average and then at 20,000 average. That's really where we're falling in. And we're running trials of efficacy on surfaces and air at those two densities. So that's the key treatment there is density concentration. So from that standpoint, what we have found thus far is that we are in the range in the 20,000 ions per cubic centimeter of air. We are having on surfaces, we have in the high 80s, like 89%, 88% effectiveness on surfaces. When we go on the other side, when we look at the aerosolized side of it, we're in the 98% effectiveness in the air with these higher densities in the 20,000 range, and that's typically within 60 minutes.
So is it fair to say when you're testing a technology like NPBI, it's critically important to make sure that the product is installed and applied properly and that the airflows and the velocities are what you would see under real-world applications?
Absolutely. You need to know how, so the manufacturers are the experts on this installation. They know how their equipment works and how it functions. And there's all these specs with it, airflow, velocity, all these different types of placement, before the coil, after the coil, you're treating the space, you're treating the coil, all those types of things when it comes to the HVAC and airflow system. So you really want to work closely with the manufacturer to get the install correct. Because if you don't, obviously all your data is going to be, spurious data. You're not going to know what, if we have efficacy, what does that mean? If we don't have efficacy, what does that mean? If we're not installed, if we're not installed like we're going to be installed in actual buildings and other types of facilities.
So not only do you have to understand the complexities of the test protocols and procedures, but you have to understand specifically how the manufacturer's product needs to be installed and applied before you can garner any results that would be considered credible.
That's correct, David. All those things have to come together. And it takes a lot of time and effort to do that. A lot of planning, a lot of verification on things, a lot of eyes from different people on how this is going to come together and work. So, you work really closely with the laboratory, you're working close with your manufacturer's engineers and the fellows who are doing the installation. All that type of thing has to be, well coordinated and well planned in order to be able to execute, to do the correct type of experiment.
So does GPS have plans to research pathogen reduction on anything other than SARS-CoV-2?
We sure do. We're going to be going after quite a few different pathogens. And these are going to range from, the cold virus, influenza, a variety of different types of viruses that, we deal with every year as a society. And then there's all these different types of bacteria, these pathogens, especially things that are, acquired in healthcare, hospital-acquired infections like MRSA, C. diff, a variety of things that we want to look at on that front too. There's some molds that are, BSL-2 type molds that cause infections like Aspergillus fumigatus and those types of things.
So now we're going to talk about how to apply and maximize needlepoint bipolar ionization with GPS founder Charlie Waddell. Charlie, please introduce yourself to the audience.
Hello, everybody. I'm Charlie Waddell, the founder and the Chief Technical Officer at Global Plasma Solutions. I'm an electrical engineer by degree. I started Global Plasma in 2008, and I've been in the ionization industry for 18 years now. I came out of the sector making the old glass tube type systems, and I wanted to create a technology that was sustainable, that was safe and effective, all within the space. And so with needlepoint bipolar ionization, we have achieved that because we have our certifications, as you've heard earlier in the presentation, UL 2998, no ozone, which means we're not creating those harmful byproducts. We also have technology that's auto cleaning and maintenance free and no replacement parts. So all of the cons of the older technology have been removed, and now it's all about the pros of the technology being safe and effective and able to treat the space.
So what has the pandemic taught us about installation and application considerations specifically with regards to NPBI?
Well, before the pandemic happened, NPVI was really used as a way to save energy and reduce ventilation air. It was also used as an alternate to UV lights to keep cooling coils clean, as well as an alternate to carbon filters to control odors that may come into a building from helicopters landing at a hospital or jets idling at an airport near a loading gate. And so the technology has now really been applied since the pandemic specifically for treating the space. We're wanting to get these into the space because that's going to help reduce the pathogens as much as possible by increasing the ion density as close to where the pathogens are now located, which we all know are in aerosol format in the actual space itself.
So for pathogen reduction, making sure we get good ion densities out into the occupied space is critical. Can you tell us why that is?
Sure. You want a high level of ions in the space because these viruses and bacteria are extremely small. So the higher the ion density, the more probability of contact with one of these viruses or bacteria. Also, this virus likes to remain suspended in the air a very long time. And as you heard from Dr. Sorrell earlier, the virus has been shown to be in the air for 3 hours or greater. And so with our newest testing that just arrived showing the aerosol data results, the technology is reducing the airborne virus upwards of 98% or more within 60 minutes.
So understanding how critical the ion densities are, can you tell us how to maximize those?
So to maximize your ion densities in the space, you need to always mount the ionization systems downstream of any filter. You know, a MERV 8 filter or a MERV 6 filter, if it's a pleated filter, it will reduce or stop the ionization. So always mount after the filter. That's number one. Number two, you need to look at where the space is in relation to where you're going to mount the ionization equipment. Because as you've heard earlier, you've got about 60 seconds for these ions to do their work before they react with each other or react with other pathogens in the air or particulates or VOCs. And so we want to be able to look at the residence time, how fast is the air moving in the ductwork, how long is the ductwork, calculate that out. And if you're approaching that 60-second mark, then you really need to look at putting the devices, the ion devices, closer to the space, typically on the supplier duct. So the closer you can get the devices to the space, the higher you can achieve the ion counts in the space. And it's a direct correlation that we're finding out between ion density and the reduction of the pathogens in the space, both on surfaces and in the air.
So Charlie, there are manufacturers of product that claim to create trillions and trillions of ions per cubic centimeter, and then there are products out there that we know make hundreds of millions of ions per cubic centimeter. Can you help us understand that dynamic a little better, please?
Sure. You know, since the pandemic started, there's been a lot of manufacturers trying to increase their ion counts, at least on paper, to make themselves look like they're going to be more effective at controlling the problem in the space. But when you get down to the science of it, currently the ion meters available in the market read up to 200 million ions per cubic centimeter, positive and negative. And so for somebody to make the claim that they're producing trillions of ions, number one, it's just a theoretical claim. There's no way to measure and verify it. And as an engineer, I'm all about measuring and verifying. So because of a lot of competitors in the market making these claims, there's no way to substantiate those claims. GPS has now adopted a new standard for measuring ionization, and you're going to start seeing this be issued within our standard specifications and our data sheets very soon. And it's called the Japanese Industrial Standard. It's not a new standard. It's been around quite a long time. As the name implies, it's out of Japan, but it's actually a test rig with a standardized test and methodology that is recognized by the American National Standards Institute, or ANSI for short. And if you go to the ANSI website, you can actually purchase and download a copy of this JIS standard, and it will allow us to compare our technology to these competitors' technologies that are claiming such high ion counts, and it will provide consistent, repeatable results. It provides, as an example, within the test, you know, the temperature range, the humidity range, the velocity that you should be operating at, the distance between the ionizer and the air ion counter. And so it takes into account all of the variables that are normally not accounted for in some of these other test protocols. And so it will be nice to be able to have everybody using a standardized test so the products can be rated to a standardized test, because we don't currently have that. And GPS is leading the way in this matter. We are going to be re-rating our products to this newest standard to the ANSI standard because we feel that is the right way to do it. And also, we will be looking at our competitors' products in the test rig and comparing our ion out to our competitors' ion output as well.
So Charlie, we've seen a lot of changes over the last 14 years with regards to GPS needlepoint bipolar ionization. Can you reflect a little bit on what you have experienced and what your thoughts are previously and then moving forward as well?
We're really thinking about ions totally different. It's not about what you're producing. It's about what you're able to achieve in the actual breathing zone in the space, because that's where the problems are right now with this pandemic, and that's what we really need to address and treat with the technology. However, we need to do that, whether it's mounting on supplier duct or looking at other options that are available out there to increase the ion counts effectively in the space, regardless of the type of HVAC system that may be applied.
So Charlie, as founder of GPS, we'd like to hear a little bit more about the company's commitment with regards to product innovation and development, the science itself, and we'd love to hear the direction that you believe both GPS and the industry are headed towards.
Great question. We are committed to developing and continuing to develop this technology in a safe and effective manner to provide the biggest impact on pathogens and particulate in the space. That's what we see as the biggest issues going forward, both with this pandemic and whatever else may be out there. And just like this seminar today, we have an expert panel of people on here that are experts in each one of their respective verticals. And I don't know of any other company, at least not in our industry, that has put together a panel like this to really address the questions that people are always asking. And myself as an engineer, a lot of these questions are outside of my field of specialty. So we have realized that Global Plasma, that we really need to bring in the proper people for the job to address these issues effectively and make people feel good about the responses we're giving them and that they are accurate and correct, no matter what field they may be in, whoever may be asking that question.
So Charlie, we understand that ventilation and filtration can be the backbone of good indoor air quality and providing proper ventilation and air quality to the space. Can you tell me how NPBI might help supplement both of those methodologies, either individually or combined?
I think they work well together. We're not trying to tell people that NPBI is the silver bullet and just go with NPBI. What we're saying is this is a good layer in the fight against SARS-CoV-2 virus. Wearing the proper masks, wearing or social distancing, having good filtration in the HVAC systems. If by some chance the virus does make its way back, you've got a good filter there that might take out a majority of it on a single pass. Good ventilation. ASHRAE as well as some other government agencies have recommended more outside air. Before the pandemic, as I mentioned, we were talking about reducing outside air, but I want to make that clear is we're not recommending reducing your outside air requirements based on adding this technology, at least not right now. A layered approach is the best approach as we try to fight this virus.
So we have been receiving a astounding number of questions from the audience, and now is the time in the presentation where we are going to address some of those. So the question has been asked, how long do ions last, and what does that mean with regards to the installation?
From my research and reading various journals, it's my understanding that ions last up to approximately 60 seconds, but any number of things in the air will react with them, from what Dr. Farahi said, the duct walls, it could be particles, it could be pathogens, anything these ions can react with will neutralize the ions. So from a design standpoint, from an engineering standpoint, I usually look at 60 seconds as the absolute maximum. And so when we're designing an HVAC system, we want to consider the length of the duct, how fast the air is moving through the duct in order for us to be able to calculate how many seconds from wherever the ion generator is mounted to getting those ions into the space will be, so we know that we have enough life left to get those ion counts up effectively in the actual space. So if you're dealing with a really large building, let's say a casino, that may have 200, 300, 400 feet of duct runs before it gets down into the casino floor, you may want to look at putting ionization units further downstream on the supply duct and boost those ion levels as they're going out into the space to make sure that we maximize the number of ions in the actual space itself.
It's a completely different conversation than those we were having just a year ago, isn't it?
It certainly is. A year ago, we were talking about how can we reduce outside air to save energy? How can we put this technology in to keep coils clean, to control odors coming in from outside? And now it's all about ions in the space, reduce my particles, reduce my pathogens.
Another question asked is, how does NPBI compare to UV? Dr. Farahi, could you tell us a little bit about that, please?
Yes, UV also is a source of giving energy to electrons, therefore it can ionize. But NPBI is very different from the perspective of producing energy to give to electrons and then give it to air. UV is primarily will be used for disinfection of surfaces, for example, when you have a stationary targets and then you want to produce ions in order to target those stationary targets. But for air quality, unless you have put UV systems inside the air conditioning unit in one way or another, okay, and if you can avoid ozone generation, because it becomes very difficult to avoid ozone generation when you use UV. You don't have control over the energy that much because the wavelength of light is fixed. But in the case of NPBI, you can change the energy, therefore you can avoid generation of ozone.
Charlie, can you touch on the commercial considerations of that a little bit for us, please?
Sure. So UV technology has historically been mounted inside the ductwork. I would say, again, pre-pandemic, upper room UV lights inside of the actual space. It looks like the bug zappers hanging up on the walls. Those weren't used that often. Typically, when UV lights were used, they were mounted over top of the drain pan and the cooling coils of the HVAC systems because that's where your biofilm and your mold grows. Now, what research has shown, two recent articles from Street Journal, one in November and I believe the other in January of this year, told us that there's no evidence of transmission of this virus through the HVAC system. So putting UV light inside the ductwork or even using higher efficiency filters inside the ductwork is not really controlling the virus. The virus is in the space, it's spreading through aerosols in the space.
What does that mean from an installation perspective of the NPBI product?
Ions last approximately 60 seconds. I've read multiple pieces of literature that discusses the physics of air ions, and 60 seconds seems to be the number that everybody has settled on. And even from my own experience measuring ions, I've not seen them last longer than that. And so with that in mind, when we're designing these HVAC systems, we want to look at where the products are mounted as compared to where the actual space is located where we want to get these ions, because within that 60 seconds, you have to understand that the ions are going to react with each other. The negative wants to go to positive and vice versa. They will react with particles, pathogens, and VOCs. They don't care what they react with. They just want to react and neutralize. And so the higher the particle counts, as an example, the lower you will generally see the ion counts because they're reacting with those higher particles. And so when we look at HVAC systems, you need to know the length of the duct or approximate length, and also how fast or the velocity is moving through that duct in order to calculate how many seconds the ions will have in the duct before they get dumped into the actual space itself. So those are some of the things that we look for when designing the system based on the 60-second life of the ionization.
So Charlie, we have a question from the audience with regards to legacy installations of NPBI technology, those that have been installed previously in the air handling unit, perhaps upstream of cooling coils. In that location, can the technology still be effective?
Yes, in that location, it will still be effective. The goal in the legacy installations was usually to keep the coils clean and also possibly to reduce your outside air requirements. And so in those installations, you're still gaining those benefits, but not knowing how deep the coil is, how many fins per inch the coil has, how dirty the coil is, and the velocity through that coil, all of that will reduce the actual ion counts. So maybe based on our latest guidance, you would want to go measure your space and confirm what the ion counts are in the space. You may have fantastic ion counts because the ionization bars do put out a massive quantity of ions. But in those spaces that may be the farthest away from the air handler, you may want to put a booster unit in, like a DM48 mounted on the duct that might feed a conference room or some other area in the building that has a high occupancy of people, so you can ensure that you still have really good pathogen and particle control at those greatest distances based on the newest guidance from GPS.
So Charlie, another question. We're beginning to see an increase in the number of articles and studies that revolve around ionization. Can you comment on any of the most current information that you've seen?
Sure. So we actually encourage third-party and peer-reviewed research by credible sources, and we especially want people that are experts in their areas. What we have found, though, is that there's no test standard with this technology, and so a lot of these researchers are actually using test methods that they're familiar with, whether it's a one-pass filter type test, which is called the ASHRAE 52.2 test, or they're trying to really relate our products to what's called the AHAM test, which gives you a clean air delivery rate number, or CADR rating, which is not applicable to a duct-mounted unit. And the CADR testing, the AHAM methodology is very clear in that. So while we do want people to do peer-reviewed studies on the technology, we also don't want them misapplying the technology, which could possibly put the technology in an unfavorable light, when in fact it does do what is claimed, because we have so much of our own independent research that's been performed over the years. And there's certainly many articles out there performed by other independent researchers that talk about how well ionization does reduce particles and it does reduce pathogens. And GPS has spent millions of dollars through many iterations to develop repeatable test methods and standards that we use internally to try to simulate real world conditions. And those tests are going to start hitting the public, and these researchers can see how we do our tests, and maybe at minimum they will be able to go out there and try to replicate what we have done and confirm that in fact what we've stated is the facts and how the technology actually works. Ultimately, we have had a few people come and talk to GPS about testing. We've not seen any testing from those people yet, but we are happy to provide our panel of experts you see here today and myself, and ask us for input on how the technology should be mounted and applied to make sure that the velocity is correct, the airflow is correct, and what you're trying to ultimately achieve with the technology is within the realm of possibility with the way the technology actually works.
So Charlie, a great last question. There are other needlepoint ionization technologies out there. What is it that makes GPS special? What is it that makes NPBI by GPS stand out above the others?
First thing that comes to mind is that we are confirmed safe from the ozone perspective. We are UL 2998 certified across our products. Also, our products are auto-cleaning. And I have seen some other companies come out with an auto-cleaning mechanism, but it doesn't physically clean the tips of the brushes. And actually, the ones that are auto-cleaning are using needles, actual metal needles, which will eventually corrode and oxidize, and they become dull. And so that alone reduces the ion output. But the fact that the cleaning mechanism doesn't clean the tip of the needle and it's just wiping the sides of the needle, and again, that relates back to the IP that we have and the way that this is done, they're going to have an inferior technology.
Thanks to Charlie, GPS, and our host of experts for helping us put on this event today, and to you, our audience, for attending and asking such good questions. Thank you. I want to give you a heads up right now. Within about a week, you will receive an email from us. On that email will be a link to a training program that we have put together for you that will cover technology, application, all kinds of things with regards to needlepoint bipolar ionization. We'll build upon what you've seen and learned here today. So by all means, when you receive that, please sign up.